I am here to read the chapter Chemistry of Lanthanoid Elements of Inorganic Chemistry of book Modern. We have learned that the element in which the last electron enters the f orbital of their atom are called f block elements. In these elements, the last electron is added to the third to the outermost called anti-penultimate energy level n-2f. These elements are also called inner transition elements because these constitute transition series within transition series d block elements. This consists of two series of elements placed at the bottom of periodic table. These two series are formed by filling of electrons. They consist of two series of elements placed at bottom of periodic table. These two series are formed by filling of electrons in 4f and 5f orbitals and are called lanthanides and actinoids respectively. The series involving the filling of 4f orbitals following lanthanum La Z is equal to 57 is called lanthanide series. The elements present in this series are called lanthanides. There are 14 elements in this series starting with serum, atomic number is equal to 58, and ending with lutetium Luz is equal to 71. The name lanthanoid is derived from lanthanum, the first member of the series. These lanthanides are also sometimes referred to as lanthanones. All these elements have closely similar properties and therefore are considered together. The reason for their similar properties is that the 4f orbitals in which the electrons are added are embedded in inner shell, while 5d and 6s electrons which have similar configuration are exposed more to the surroundings. Because of their similar physical properties, their separation and identification proved to be very difficult task. The first stage in their separation was to get them as oxides. However, the occurrence of oxides of lanthanoids was very rare. Therefore, these elements have also been called rare earth elements. Nowadays, the term rare earth is not used. Their substantial deposits occur in Scandinavia, USA, USSR, and India. General characteristic of lanthanides. The important general characteristic of lanthanides are described below. Electronic structure and position in periodic table. The lanthanoid involves the gradual filling of 4f orbitals. It may noted that energy of d orbitals and the next inner shell f orbitals are closely similar and therefore the order of filling the 4f orbital in atom shows quite irregularities. At lanthanum Z is equal to 57, both 5d and 4f orbitals become stable due to increased effective nuclear charge as a result of poor shielding effect of 6s electrons. Therefore, it is observed that at lanthanum the incoming electron enters the d orbitals and its electronic configuration is La Z is equal to 57 xenon 5d1 6s2. However, as we move further after La, the energy of 4f subcell become lower than the 5d subcell, and therefore the next electron in serum enters the 4f subcell. The electronic configuration of serum is Ce xenon 4f2 6s2. The filling of 4f orbital continues till we reach ytterbium in which the 4f subcell get completely filled. Now, after 6s and 4f subcell have been filled, the next electron goes to 5d subcell. The configuration of lutetium is xenon 4f14 5d1 6s2. This constitutes lanthanoids. The general electronic configuration of lanthanides may be written as xenon 4f0 to 14 5d0 to 1 6s2. There are the element lanthanum, cerium, praseodymium, neodymium, promethium, cermium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thallium, ytterbium, lutetium are lanthanoids. Physical properties. The important physical constant of lanthanoids are given. These are discussed below. Ionization energy. The lanthanides have fairly low ionization energy. In general, the first and second ionization energy of lanthanoids increase with increase in atomic number. The first property and second ionization The first and second ionization energy of lanthanoids increase with increase in atomic number, but the variation is small and irregular. The variation of ionization energy with atomic number is shown below. It is clear from figure that some deviation are observed in regular increasing order such as EU, ZD, ytterbium, lutetium. These are attributed to the stability of half-filled and completely filled F subcell. The first ionization energies are order of 560 kilojoule mole inverse, and second ionization energies are order of 1150 kilojoule per mole. These values are quite comparable to alkaline earth metals, especially calcium. Ionization energy 1 589 kilojoule mole inverse, ionization energy 2 1145 kilojoule mole inverse. Melting and boiling points. Lanthanides have fairly high melting and boiling points. However, the melting and boiling points do not show any regular trend as we move from La to Lu in the series. Inspection of table 4.2 shows that europium and ytterbium have unexpectedly low melting and boiling point. These atoms form Eu2 positive and Yb2 positive ion and result in weaker metallic bonding because there are less than 3 electrons per atom in the metallic bond. The other lanthanoid atoms gives 3 electrons per atom in the metallic bonds. Therefore, melting and boiling point of Eu and Yb are low as compared to the value for the other lanthanoid elements. Density. The densities of lanthanides are low, which range between 6.7 to 9.74 gram per centimeter cube. However, there is no definite trend in the density value of lanthanoids with increase in atomic number. Eu and Yb have unexpected low values. Heat of fusion and heat of vaporization. The heat of fusion and heat of vaporization also do not show definite trend with increase in atomic number. Electronegativity values. The electronegativity values of lanthanoids between 1.0 to 1.15 are quite close to those of alkali and alkaline earth metals. Therefore, lanthanides are expected to form ionic compounds. Electropositive character. Because of low ionization energy and low electronegativity value, the lanthanoids are electropositive like S block elements. Oxidation state. The common oxidation state of all the lanthanoids is +3. In addition, some lanthanoids show +2 and +4 oxidation state also. They are shown by those elements which by doing so attain the stable F0, F7 and F14 configurations. For example, number 1. Cermium Mtb exhibit +4 oxidation state. Cermium and terbium attain F0 and F7 configuration respectively when they get +4 oxidation state. Eu and Yb exhibit +2 oxidation state. Europium and ytterbium get F7 and F14 configuration in +2 oxidation state. La, Zd and Lu exhibit only +3 oxidation state. These elements show +3 oxidation state only because by losing 3 electrons they acquire stable configuration of empty half filled and completely filled 4f subcells. Exceptional example. Some other examples show +2 and +4 oxidation state even though they have electronic configurations other than F0, F7 or F14. For example, Sm and Tm show +2 oxidation state having F6 and F13 electrons respectively, in which they have 1 electron less than half filled or completely filled configurations. Similarly, Pr, Nd and Dy show +4 oxidation state having F1, F2 and F8 electronic configurations. The stability of unusual oxidation state may be dependent upon some other thermodynamic and kinetic factor which are significant importance, but these are less stable than +3 state, which is characteristic of this family. The outermost electronic configuration of lanthanoid in different oxidation state is given below. Color and spectral properties. The lanthanoid are silvery white, but many lanthanoid ions are colored both in the solid state and in the aqueous solution. The colors remain same even on the change of an ion. Therefore, the color are characteristic of lanthanoid ions. The color of ions depend upon the number of unpaired electrons because it has been observed that the ions containing NF electrons have almost similar color to those with 14 minus NF electrons. The different ion having NF and 14 minus NF and their color are given below. Ions are La3 positive, number of 4f electrons 0, color colorless. Pr3 positive, number of 4f electron is 2, color is green. Pm3 positive, number of 4f electron 4, color pink. Lu3 positive, number of 4f electron 14, color colorless. However, it has been observed that some Di and tetra positive ions having same number of electrons, isoelectronic ions. However, it has been observed that some Di and tetra-positive ions having same number of electrons, isoelectronic ions as tri-positive ions do not have same color. For example, Sm2 positive and Eu3 positive have similar number of unpaired electrons, but they have different colors. Some other examples are given in table 5. The color of lanthanoid ion arises due to absorption of light from visible region of the spectrum, resulting in the electronic transition within the 4f level FF transition. A remarkable characteristic of spectra of tri-positive lanthanide ion is that the absorption band are extremely sharp line-like band in ultraviolet, visible or near infrared regions. Many of these bands are line-like and become even narrower as the temperature is lowered. This behavior is in contrast to absorption band of DD transitions, which have broad absorption bands and become even narrower as the temperature is lowered. This behavior is in contrast to absorption bands of DD transitions, which have broad absorption band. The band of lanthanide ion are sharp that they are useful for characterizing the lanthanide ions. The main reason for very sharp absorption band is that the 4f orbitals lie deep in the atom of these elements. Therefore, they are effectively shielded from the surroundings by overlying 5s and 5p orbitals, and consequently the absorption band arise mainly from electronic transitions within the 4f levels. Thus the absorption bands show little dependence on the nature of ligand. In addition of FF transitions, sometimes color of lanthanoid ion is attributed to FD transitions. The FF absorption transition of lanthanide ion have low intensity because they are not allowed, where FD transition are not allowed. In contrast to FF transition, the FT transitions are allowed and hence show very intensive absorption band. For example, FD transition absorbed for Ce3 positive and Tb3 positive are very intense. Magnetic properties. All the lanthanoid ion with the exception of La3 positive, Lu3 positive, Ce4 positive and Yb2 positive ions are paramagnetic. Because they contain unpaired electrons in their 4f subcells, the ion La3 positive, Lu3 positive and Ce4 positive and Yb2 positive, because they contain unpaired electrons in their 4f cell, which have 4f0 and 4f14 electronic configuration, are diamagnetic because they have no unpaired electrons. The magnetic properties of lanthanides are different from those of the transition element. As we know, the magnetic moment arises from two types of motion of electrons. The spin motion of electrons around its own axis produce magnetic moment called spin magnetic moment, while the orbital motion of electron around the nucleus produce magnetic moment called orbital magnetic moments. The observed magnetic moment of a substance is due to the contribution of same the spin moment and the orbital moment. In case of transition elements, d block elements, The magnetic moment mainly corresponds to the spin-only magnetic moment. This is due to the fact that the d orbitals are not well shielded from the environment and take part in the bond formation with the ligands, atoms, ions, or molecules. As a result, the d electrons of metal interact strongly with the ligands surrounding the metal ions. Due to the electric field of ligands, the orbital motion of electron gets restricted and thereby the orbitary moment of these electrons gets quenched. The magnetic moment of d block elements thus arise mainly from the contribution of spin motion of electron only. The spin only magnetic moment is given as mu spin only under the root n into n plus 2, where n is the number of unshared pair electrons. This relationship gives almost correct value of magnetic moment for d block elements. However, the above relationship is not valid in the case of f block elements. In these elements, the 4f orbitals are well shielded from the surroundings by the overlying 5s and 5p subshell. As a result, the electric field of ligand surrounding the metals ion does not restrict the orbital motion of electron. Thus, orbital contribution is not quenched. Therefore, the magnetic moments of lanthanoid ion is due to the both electron spin and orbital motion of electron. They may be calculated from the relation mu is equal to under the root 4s into s plus 1 plus L into L plus 1, whereas S is the resultant spin quantum number and L is resultant orbital quantum number. The theoretically and experimentally observed magnetic moment values are given below. The magnetic moment of lanthanides depend on the atomic number and the number of unpaired electron. Unpaired electron for the ions La3 positive, Zd3 positive and Lu3 positive. The magnetic moments correspond to spin only values. For these configurations, there is no orbital angular momentum. L is equal to 0. The above expression becomes under the root 4s into s plus 1. The magnetic moment may be calculated only on the basis of spin only value. Here S is equal to ns, where n is the number of unpaired electrons, s is spin quantum number. Configuration, there is no unpaired electrons and n is 0 and their magnetic moment is also 0. The magnetic moment can be calculated on the basis of spin only value because orbital angular momentum is 0. Zd3 positive, xenon 4f7. Number of unshared electrons n is equal to 7, s is equal to 1 by 2. Small s is equal to 7 into 1 by 2 is equal to 7 by 2. Mu is equal to 4s into s plus 1. This can also be calculated as mu is equal to under the root n into n plus 1. 7 into 7 plus 2 is equal to 9 is equal to under the root 63 gives 7.9 bm. The magnetic moment of tripositive lanthanoid ion are plotted. La3 positive and Lu3 positive are dimagnetite, no unpaired electrons. It is observed that the value increases up to neodymium and then decreases to 1.47 for Sm3 positive ion. It increases again and reaching a maximum value for dysprosium and holmium. Thereafter, it start decreases and becomes 0 for lutetium, which is dimagnetic. Ionic radii, lanthanoid contraction. We know that we move down a group, atomic size normally increases. This mainly due to the additional cells or electron between the successive periods. However, as we move across a period from left to right, atomic size decrease. This is attributed to the increasing effective nuclear charge, as a result of which the outermost shell of electron is attracted more and more. Consequently, the size decreases. For example, the covalent radii of alkali metals increase from Li to Cs and for halogens from F to I. If we consider the ionic radii of lanthanoid, we get very interesting observation. For comparison sake, we can take the ionic radii of trivalent ions M3 positive, which are most stable. These are shown in figure 3. It is clear that ionic radii decrease from one element to another in the lanthanoid series, but decrease is very small. It has been observed that from Ce3 positive to Lu3 positive, the ionic radii decrease from 1.03 angstrom to 0.86 angstrom. Obviously, for an increase of atomic number 14, the decrease in an ionic radii is only 0.17 angstrom. This is very small decrease in comparison to elements of other groups and periods. Similarly, on moving from Ce to Lu, the atomic radii also decrease from 1.65 angstrom to 1.56 angstrom, and the decrease is only 0.09 angstrom. This small steady decrease in ionic and atomic size of lanthanoid elements with increase in atomic number is called lanthanoid contraction. Cause of lanthanoid contraction. In lanthanoid series, the 4f electrons are being added one at each step. As we move from one element to another, the shielding of one f electron by another from the nuclear attraction is quite weak due to the shapes of f orbitals. The nuclear charge, however, increases by one at each step. Hence, with increasing atomic number and nuclear charge, the effective nuclear charge experienced by each 4f electron increases. Hence, the inward pull experienced by 4f electron increases, and this causes a reduction in the size of atom or ion. The sum of the successive reduction gives the total lanthanoid contraction. Consequences of lanthanoid contraction. Lanthanide contraction has a very significant effect on the relative property of elements which precede and which follow the lanthanides in periodic table. Some above important consequences of lanthanoid contraction are given below. Number 1. Steady decrease in size. There is regular decrease in the ionic radii of lanthanoids. Electronegativity. There is slight regular increase in electronegativity of trivalent ion. Electrode potential E0 values. This is small but smooth increase in standard electron potential value E0 for the process.